Hey, welcome back. Last time, we started to talk about propositional logic, and we introduced truth tables. Truth tables are a tool that we can use to evaluate the truth values of compound proposition for any combination of the truth values of the propositional variables inside the compound proposition. And last time, we saw some examples of truth tables. We saw them for negations, conjunctions, disjunctions, and some other compound propositions. We're going to see some more examples in this video. And we're also going to learn about more terms in propositional logic, including tautologies, contradictions, logical equivalences. We'll also learn De Morgan's laws, and we're going to learn about satisfiability as well. So to start out, let's look at some more truth tables. So we're going to do a truth table for this proposition right here. And the proposition is P and Q implies R. So our propositional variables inside this proposition are P, Q, and R. And I'm going to put a row which will have the labels for each column. We'll have a column for each propositional variable. And we're going to take the compound proposition that we have at the top, and we're going to break it down into smaller propositions. And we're going to evaluate the truth values of the smaller propositions and use those to build the whole compound proposition that we want up here. So to start out, we need to write all the combinations of the truth values of the propositional variables. And we could do this before or after we write out all of the propositions inside this proposition, but we'll do it before. So we can start with TTT. And we can really write these in any order. I'm just choosing this order. And notice again, we have three propositional variables here. And I encourage you, if you want to do this problem for practice, it's a good time to pause here and fill out the table yourself before seeing the rest of the table. So now that we have all the rows of the table, we'll write out the sub propositions of the compound proposition up here. So one of the sub propositions is just R, and we already have a column for R right here. So this R, we've already done it in that column, so that's good. There's also a sub proposition right here, the P and Q. And we can put a column for that, so we'll put it right here. So we have a column for P and Q, we have a column for R, and that'll be enough for us to evaluate the column P and Q implies R. And so now we can start by evaluating the truth values for P and Q. So the first row, we have P is true and Q is true, and that gives us P and Q is true. Second row, we have the same thing for P and Q. P is true and Q is true. The difference with the first row is that R is false, but there's no R in this column. It's just P and Q. So it's still true, just like the first row. The next row, the third row, we have P is true, but Q is false. So P and Q, the conjunction, that's going to be false. Fourth row is the same. P is true, Q is false. So P and Q, that's going to be false. Fifth row, we have P is false, but Q is true. So it's like the opposite of the third and fourth rows. It's still false for the conjunction. Same with the sixth row. P is false, Q is true. We get false. And then the last two rows is the same for both. P is false, Q is false. So we get false for both of these. And now we have enough to do this last column. So P and Q implies R. P and Q, we can check the values for each row. And this first row, we have P and Q is true and R is true. And if the hypothesis, so this right here is the hypothesis of the implication, and this is the conclusion. So if the hypothesis is true, then the conclusion has to be true for the implication to be true. And here they're both true. So we can write it true right there. In this second row, the hypothesis P and Q, that's true, but the conclusion R is false. So that means the implication is false. Now we can check the third row. In the third row, we have P and Q is false and R is true. So the hypothesis is false, but the conclusion is true. Whenever the hypothesis is false, the implication will always be true. So the conclusion can be true or false, and the implication will be true as long as the hypothesis is false. And since the hypothesis is false here, since P and Q is false, then the implication is true. And now we can look at the fourth row. And the fourth row, we have P and Q is false and R is false. So again, the hypothesis is false and the conclusion can be anything since the hypothesis is false. So the implication again is true. And we notice for the rest of the rows here, P and Q, it's always false for all the rest of those. And that means the hypothesis is always false for the rest of those rows. And since the hypothesis is always false for those, it means the conclusion can have any truth value. It means R can have any truth value. And regardless of the truth value of R, the implication will be true. So this row is true. This row is true. This row is true. And this row is true. So that is our first truth table. And we've evaluated all the possible truth values of this compound proposition at the top. in terms of the truth values of the propositional variables inside the proposition. And the propositional variables were P, Q, and R. Again, there were three of them. We had three propositional variables, and 2 to the third, that equals 8. And we had 8 rows here. And the number of rows is always going to be 2 to the number of propositional variables. So now that we finished this truth table, let's look at another one. So this one will have the same number of rows as the last one. So we'll have a column for P, column for Q, and a column for R. And we'll have a column for P and Q. And then we'll have a final column for P and Q and R. And as before, we will have 8 rows of truth values because 2 to the third is 8. Okay, I think that's all of them. So now let's evaluate the truth values for the conjunction P and Q. So in the first row, P is true and Q is true. So P and Q is true. And this is the same one as the last slide. So we can also just remember what we did in the last slide. We have a true here as well, because the first and second rows are the same for the P and Q. And then the rest of these were false. And now we can do that final column, the conjunction for all three. So the first row, the conjunction P and Q is true, and R is also true. So the conjunction P and Q and R, that's going to be true. Second row, the conjunction P and Q is true, but R is false. So the conjunction P and Q and R is false. Third row, the conjunction P and Q is false, and R is true, but the conjunction P and Q and R is false, because they both have to be true for the conjunction to be true. And we can notice all of these rows, P and Q is false, and the conjunction P and Q and R, for it to be true, both of the conjuncts have to be true. And P and Q being false makes it false for all of these rows. And we finished the truth table there. So that's the final column for the truth table. So we only got a single true, and all the rest were false. So we'll do one more example before we move on to some new terms. So this will be another one with 3 propositional variables. And then this time we have some different subproposition. So again, we have R, but P implies Q. We didn't have that one before. And then our final proposition, P implies Q implies R. And now we can fill out the rows. So that gives us all the rows. And now we just need to fill out these last two columns. So P implies Q. This first row, we have P true, and we also have Q true. So P implies Q in that case is going to be true because both the hypothesis and the conclusion are true. Second row, same thing. The values for P and Q are the same, so we get true again. Third row, P is true, but Q is false. So the hypothesis is true, but the conclusion is false. Thus, the implication is false. Fourth row, we have the same thing as the third row, so we got false again. Fifth row, P is false and Q is true, so the hypothesis is false, but the conclusion is true. And whenever the hypothesis is false, the conclusion can have any truth value and the implication will be true. So this is true. And the last few rows will also be true because, again, the hypothesis P is false for all of these last four rows. And now we can do this last column, the larger implication. P implies Q implies R. So here, our hypothesis is P implies Q, and our conclusion is R. And for the first row, P implies Q is true and R is true. So the hypothesis is true and the conclusion is true. So the implication, that's true. Second row, we can see the hypothesis, P implies Q, that's true. The conclusion, R, in this case, is false. So hypothesis is true, conclusion false. That means the implication is false. Third row, P implies Q. That's our hypothesis. That's false. The conclusion, R, is true. And when we have the hypothesis false, the conclusion can have any truth value and the implication will be true. So in this case, the implication, P implies Q implies R, that's going to be true. Fourth row, the hypothesis P implies Q, that's false. And the conclusion, R, that's also false. And when the hypothesis is false, the conclusion can have any truth value and the implication is true. So since the hypothesis is false here, P implies Q is false, that means that this implication, P implies Q implies R, is true. Okay, now we're on to the fifth row. So in the fifth row, we have the hypothesis P implies Q is true, and the conclusion R is true. They're both true, so the implication is true. Now we're on to the sixth row. Sixth row, the hypothesis P implies Q is true, but R is false. So the hypothesis is true, but the conclusion is false. So in this case, the implication is going to be false. And now we only have 2 rows left. So 7th row, our hypothesis, P implies Q. This is true here. And the conclusion, R, is also true. So the implication is true. And finally, the last row. The hypothesis P implies Q is true. The conclusion R is false. So the implication in this case is going to be false again. And that completes our last column. So this gives us all the truth values for the implication. P implies Q implies R. So now we're going to go on to some other topics. And as we look at some new terms and see some examples, again, feel free to pause at any point so you can work through the problems yourself before I fill out the details. So here's a new term. And a tautology is a compound proposition which always has the truth value true, which we denote T, regardless of which row of the truth table we look at. In other words, regardless of which truth values that we assign to the propositional variables inside the compound proposition. And in order to illustrate tautologies, we're going to look at some examples and we're going to determine whether or not they are tautologies. So I'm not saying ahead of time that these are tautologies, but we're going to figure out whether they are. So here's this first one. And to check whether something is a tautology, in order to determine whether something is true for all possible combinations of truth values of its propositional variables, we already have a tool that we can use to do that. And the tool is truth tables. So we're going to make a truth table for each of these potential tautologies to determine whether or not they actually are tautologies. So let's do a truth table for P implies P. This truth table is especially small because this proposition only has a single propositional variable, P. And we only have 2 columns in this table, the P column and the P implies P column. And we only have 2 rows because 2 to the 1. So P can be true or false. And when P is true, the hypothesis is true, the conclusion is true, so the implication is true. And when P is false, the hypothesis is false. And as we've seen, whenever the hypothesis is false, the conclusion can have any truth value. And regardless of the truth value of the conclusion, the implication will still be true as long as that hypothesis is false. So in this case, P implies P, it's still true. So this one is a tautology. It's always true, regardless of the truth values of the propositional variables. So we're going to look at another example. This one has a slightly larger truth table because we have 2 propositional variables now, P and Q, and we have a subproposition besides the propositional variables. And that subproposition is P or Q, the disjunction. And we have one last column here for the proposition that we're trying to determine whether or not it is a tautology. So we have 4 rows of truth values here because 2 squared is 4. we have true, 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 false, false, true, and false, false. And the disjunction is going to be true as long as at least one of the disjuncts is true. So P or Q, when P is true and Q is true, the disjunction is true because they're both true in that case. When P is true and Q is false, at least one of the disjuncts is true, P, so the disjunction is still true. Same with the third row, Q is true there. Even though P is false, the disjunction is still true because Q is true. This last row, the disjunction is false because both of the disjuncts are false. P and Q are both false. And now we can evaluate the final column. P or Q implies, supposed to be a P. I wrote a Q there. I guess it doesn't really make much difference, but I'll change it to the one that we actually want to do. So P or Q implies P. So first row, our hypothesis P or Q is true, and our conclusion P is also true. So the implication is true. Second row, the hypothesis P or Q still true, and the conclusion P is still true. So this one's true. Third row, the hypothesis P or Q, that one's true, and the conclusion P is false. So the hypothesis is true, but the conclusion is false. So that means the implication is false. And we don't even have to do that last row. We can, but we don't have to do it at this point because we're just trying to determine whether or not this is a tautology. So we could stop here, but we'll do that last row anyway. So that last row, P or Q is false, the hypothesis is false, and the conclusion is also false. As long as the hypothesis is false, the implication is going to be true, regardless of the truth value of the conclusion. So here, the implication is true, but it's not a tautology because of this row. So this is not a tautology. And we're going to look at one more example. This one has a truth table with the same dimensions as the last example. The only difference is that third column. So we only have 4 rows again. We can evaluate that third column. When P is true and Q is true, the conjunction is true. The rest of the rows, the conjunction is going to be false though. And that's because in the rest of the rows, at least one of the conjuncts is false. And for a conjunction to be true, both conjuncts have to be true. So only one row, the top row, has the conjunction true. Now the implication, this last column. For the first row, P and Q is true, so the hypothesis of the implication is true. And P is true, so the conclusion of the implication is true. So the implication is true. Second row, P and Q is false, so the hypothesis of the implication is false. Whenever the implication has false hypothesis, then the implication is true, regardless of the truth value of the conclusion. So here, our hypothesis is false, and the conclusion is true, and the implication is true, because that hypothesis is false. And same with the rest of the rows, the hypothesis is false for all of those. So the implication is going to be true for all three of these. And we're only looking at the hypothesis there. We can completely ignore the conclusion. As long as the hypothesis is false, the implication is true, regardless of the conclusion. So we got this last column, all truths. So this is a tautology. And I think that's the last example of tautologies. So this next one, looks like I wrote the wrong header for that, but the definition's fine, so just ignore that. So this is about contradictions. A contradiction is another kind of compound proposition. And instead of always having the truth value true, like tautologies, it always has the truth value false, which we denote F. And it has the truth value false in every row of the truth table. In other words, regardless of which truth values that we assign to the propositional variables, we always get false in a contradiction. So like we did with tautologies, we're going to look at some examples of compound propositions, and we're going to do their truth tables to determine whether or not they are contradictions. So here's the first one, and this one has a pretty small truth table because it only has a single propositional variable. We'll do a column for each of the sub-propositions. So one of our sub-propositions is just that propositional variable P. Another sub-proposition is the negation of P. And finally, the compound proposition that we're looking for, the conjunction P and not P. We have one propositional variable, so we only have two rows, 2 to the 1, in our truth table. And we have a row when that variable is true, and we have a row where it is false. Whenever the propositional variable P is true, then the negation of P is false. And when P is false, the negation of P is going to be true. Now we're able to evaluate the final column, the conjunction. In this first row, we have P true, we have not P false. So the conjunction P and not P is going to be false. Second row, we have P false, not P true. So the conjunction P and not P, again, is false. So this is a contradiction. So let's look at some more examples. Okay, this one. Let's try to determine whether or not this is a contradiction. So this one looks more complicated than some of the other ones we've seen. So even though it won't have too many rows, it will have a decent number of columns. So first, we'll have the columns for our propositional variables P and Q. Then we need a column for their negations, not P and not Q has a column. And then we're going to have a column for the disjunction P or Q. And then we'll have a column for the disjunction not P or not Q. And then finally, all the way over here, we'll have a column with the proposition that we're looking for. P or Q conjunction, not P or not Q. Okay, so let's fill out this truth table. Starting out, we need to fill out those first two columns with all the possible truth values that we can assign to P and Q. So true, true here, true, false here, false, true here, and false, false here. Okay, now we can do the column for not P. When P is true, not P is false. When P is false, not P is true. So we have TTFF in that P column. So it's going to flip in this not P column. We're going to get FFTT. Now this Q column, we have TFTF over here. In the not Q column, it's going to flip. So instead of TFTF, we're going to get FTFT. Now we can evaluate the disjunction P or Q. First row, we have P true and Q true. So P or Q, it's going to be true. Second row, P is true and Q is false. So the disjunction is still true because only one of them has to be true. They can both be true, but you only need one. So P being true is enough. Third row, we have P false, but Q is true. So the disjunction is still true. That last row, though, the disjunction is going to be false because both disjuncts are false. P and Q are false. So now we'll do this second to last column. So the second to last column, the disjunction is not P or not Q. So we need to focus on these two columns here. So those two columns, oh, whoops, these two, I marked the wrong two. These, yeah. So we're gonna look at those two because those are our columns for not P and not Q. So first row, not P is false, not Q is false. So the disjunction, not P or not Q, that's going to be false because both disjuncts are false. Second row, not P is false, not Q though is true. So the disjunction, not P or not Q, that's going to be true. Third row, not P is true, not Q is false. So the disjunction is true because the not P is true. And final row, they're both true, not P and not Q. These are both true. So the disjunction is going to be true. And now, finally, we can evaluate this last column. So this last column is a conjunction. So the first row, the conjunction P or Q and not P or not Q. So the P or Q, the left conjunct is true here. The right conjunct, however, is false. So the conjunction is going to be false. Because for the conjunction to be true, we need both conjuncts to be true. Second row, the left conjunct is true. P or Q, that's true. The right conjunct is also true. So the second row, the conjunction, is going to be true. And this example, we were checking whether or not it was a contradiction. And so we see already that this is not a contradiction, because for something to be a contradiction, it has to have every row false in the truth table. And we just found a row where the truth value is true. So we don't really need to finish this truth table. We will anyway, but we could stop here and say not a contradiction. So here, the third row, P or Q is true. Not P or not Q is also true. So the conjunction is going to be true. In this final row, P or Q is false. Not P or not Q is true, but the conjunction is false, because both conjuncts would have to be true for the conjunction to be true. So it's not a contradiction because there are rows where the truth value for this proposition is T, T for true. Okay, so I think we have one last example. So that's our last potential contradiction. But in order to determine whether or not it's a contradiction, we will fill out its truth table. Again, we have a proposition with two propositional variables, a P and a Q. We'll have a column for not P. We'll have a column for not Q. We'll have a column for P or Q. We'll have a column for P or Q and not P. And then finally, we'll have a column for P or Q and not P and not Q. So that's our final column. So it barely fits into there. And notice what I did here again is I just took all the smaller propositions in this. I just listed all of them and I put them in my table. And I put them roughly in order of how I want to build them. But really, I could have put them in any order here because it's not like I have to fill the columns in order from left to right. I could skip around if I wanted to. So feel free to put the column headers in any order you want. You just need to have some column that computes the one that you're looking for. So we want to figure out whether or not this is a contradiction. We need to look at all the possible truth values for P and Q. We'll do the columns for not P and not Q again. And then our disjunction here, P or Q, it's true here, true here, true here, and false there. The only row where it's false is the row where both disjuncts are false. All the other rows, at least one of the disjuncts is true. At least one of P or Q is true in all the top three rows. And now we can do this conjunction, P or Q and not P. So here in the first row, the left conjunct, P or Q, is true. The right conjunct, not P, is false. So the conjunction P or Q and not P, that one is going to be false. So for the conjunction to be true, both conjuncts have to be true. And since we have one of the conjuncts false there, the conjunction is going to be false. Second row, our left conjunct, P or Q, is true. The right conjunct, not P, this one is still false. So the conjunction P or Q and not P, still going to be false because one of the conjuncts is false, the not P. Now the third row. Third row, P or Q, that's still true. So the left conjunct is true. The right conjunct, not P, here is true. So the conjunction is true because both conjuncts are true. And final row, P or Q, that's false. Not P is true. And that means that the conjunction is false because one of the conjuncts is false here, the left conjunct. And now we can move on to the last column. So last column, we have an even larger conjunction, P or Q and not P, and not Q. So our left conjunct here is P or Q and not P, and the right conjunct is not Q. So in the first row, our left conjunct is false, and our right conjunct is also false, so the conjunction's false. Second row, the left conjunct is false, the right conjunct is true, the conjunction's false because both conjuncts would have to be true for the conjunction to be true. Third row, the left conjunct is true, the right conjunct is false, so the conjunction is false. And last row, the left conjunct is false, the right conjunct is true, the conjunction's false because one of the conjuncts is false. So that means this last column, everything is an F. They're all false, regardless of the truth values of the propositional variables. So this is a contradiction. So now we can move on to another term. So this term is logical equivalence. And the terms that we just talked about, tautologies and contradictions, these are terms that were describing a single proposition. This term, logical equivalence, describes two propositions. And if we're given two propositions here, I wrote compound propositions. They don't necessarily have to be compound. So could be an atomic proposition, one of them could be. And we say that P and Q are logically equivalent if P biconditional Q, in other words, P if and only if Q, is a tautology. I'm going to cross that out. So if we want to check whether or not two propositions are logically equivalent, we just need to check whether or not this proposition right here is a tautology. We can actually do it in an even simpler way. We don't even need to write this one out right here. We can just do a truth table for P and a truth table for Q. And we can see if the columns that we get at the end are identical. So that's how we're going to evaluate logical equivalence for several examples. And we'll also see another way that we can demonstrate logical equivalence. So here's one. So we're going to demonstrate the logical equivalence here using truth tables. We can do this all in one truth table. And we should have a column between them. So we can look at not P here. We can write it like that to make it a little clearer. And that tells us we should have a column for the not P. And then we'll have our last column, the not P. So we only have a single propositional variable here, the P, and that means there's only two rows for the truth values, T or F. And when P is true, not P is false. When P is false, not P is true. And then not P. When not P is false in the first row, not P is going to be true. And when not P is true, the second row, then not P is going to be false. So we can look at the column for P. There's that column. And the column for not P, that column. And we can see they're identical down here. So here, same letters in the same order. So these are logically equivalent. Let's look at some more examples. Okay, so we're going to do the first De Morgan's law here. This one has two propositional variables, so we're going to have more rows than the last table. We'll put it all in one table. So we want to see, is this one logically equivalent to this one? And it has a name, so the answer is going to be yes, but we got to prove it with the truth table. So we're going to write all the possible truth values for the P and the Q. And we'll fill out that column for the disjunction. And we'll do the columns for the negations. And these are all like columns that we've done before in other tables. So that's why I'm spending a little less time on these. And now this column, let's look at this one. Not P or Q. So in the first row, P or Q is true. So not P or Q is going to be false. Second row, P or Q again is true. So not P or Q is going to be false. Third row, P or Q is true. So not P or Q, false. And finally, the last row, the P or Q is false. So the negation, not P or Q, that's going to be true. Now we can do this last column. The last column is not P and not Q. So in the first row, not P. So we have the not P column and not Q column there. So the first row, not P is false, not Q is false. So the conjunction, not P and not Q, is going to be false. Second row, the not P is false, the not Q is true. The conjunction is going to be false, because for the conjunction to be true, both conjuncts would have to be true. Third row, not P is true, but not Q is false. So the conjunction again is false. Finally, in the last row, both not P and not Q are true. So the conjunction is going to be true. So we can look at these last two columns. We got FFFT in both of them. So these are logically equivalent propositions. And that is the first of De Morgan's laws. Let's look at another one. So this one, the table is going to look pretty similar. Just some different sub-propositions. And we can fill out these negation columns, same as we've been doing. And now we have a conjunction column, P and Q. Conjunction is going to be true in that first row because both of the conjuncts are true. All the other rows, at least one of the conjuncts is false. So the conjunction will be false in all the rest of the rows. Then we do the negation of that same conjunction that we just did. In the first row, the conjunction is going to be true, so its negation is false. Second row, the conjunction is false, so the negation is true. The rest of the rows, the conjunction is false, so its negation is true. Now we go on to that last column. Not P or not Q. First row, not P is false, not Q is false, so the disjunction is false because neither of the disjunctions is true. Second row, not P is false, not Q is true, so the disjunction is true because at least one of the disjuncts is true. Third row, not P is true, not Q is false, so the disjunction is true. And in the last row, the disjunction is still true, and in that case, they're both true. Not P and not Q are both true. We notice these last two columns are identical, FTTT. So these are logically equivalent. So that's the other De Morgan law. So here's another one. So I'm just looking at both of these propositions here. I'm going to take all of the sub propositions inside of them. I'm just going to build them up. So we have a not Q over here. We have a P implies Q over there. And then we have a P and not Q over here. And then we have the not P and not Q. That's the last one we have to do. So that's everything. So now we can do the truth table. Okay, so here we need to do the not Q. We've done this one a bunch of times already. P implies Q here. In the first row, hypothesis is true, conclusion is true, so the implication is true. Second row, the hypothesis is true, but the conclusion is false, so the implication is going to be false there. Third and fourth row, the hypothesis is false in both of those rows, so regardless of the truth value of the conclusion, the implication is going to be true. So that's that column. On to the next column, P and not Q. First row, P is true, not Q is false, so the conjunction P and not Q is false, because one of the conjuncts is false. Second row, P is true, not Q is true, the conjunction is true, because both conjuncts are true. Third row, P is false, not Q is also false, so the conjunction is false. And the final row, P is false, not Q is true, conjunction is false. For the conjunction to be true, we need both conjuncts true. It only happened in the second row. Now that last column, not the conjunction. So not P and not Q. First row, we have P and not Q is false. So its negation, not P and not Q, is going to be true. Second row, the conjunction P and not Q, that's true. So the negation, not P and not Q, is going to be false. So we're just taking the truth values here and we're flipping them over there. So T here and T there. So we're just negating. And we want to check whether these two propositions were logically equivalent. And we have one of them here, TFTT, and the other one right here. And it's the same, TFTT over there. So these are logically equivalent. And now that we did that with a truth table, let's see how we could have evaluated that without a truth table. So we've seen before that P implies Q is logically equivalent to not P or Q. So we saw that in the previous videos. And if this is logically equivalent, we can combine this with one of the facts that we just proved in this video. So we saw that using De Morgan's law, so we can apply De Morgan's law to something that's equivalent to this one. So we want to say that not P or Q is equivalent to something that we can apply De Morgan's law to. So we'll say this is logically equivalent not P or not Q. So we showed a few slides ago that a proposition and its double negation are logically equivalent. So Q is logically equivalent to not Q. And now we have this to work with. And we can say that not P or not Q is logically equivalent to, and this is where we can use De Morgan's law. We can say this is logically equivalent to not, and then we're just taking this not off of each of these disjuncts, and we're changing the disjunction to a conjunction inside the parentheses. So we took a not off of the left disjunct to get a P. We have a conjunction there, and a not off of the right disjunct to leave us with a not Q. This is by De Morgan's law. And this is because Q is logically equivalent to not Q. And this one, the one at the top, so we're using 3 facts here. So we showed that these were logically equivalent with the truth table. So this one is logically equivalent to this one. We saw that with the truth table. We can also see it just by using this string of logic. So we have 3 facts here. We started with this left proposition, this one up here. P implies Q is logically equivalent to not P or Q. And that we talked about in the last video. And then we took this one, not P or Q. That's logically equivalent to not P or not Q. And then we took this one, not P or not Q, and that's logically equivalent using De Morgan's law to not P and not Q. And that is the one that we were trying to get over here. And each of these logical equivalences is saying that the truth table for P implies Q, that column has the exact same truth values as the column for not P or Q. And the column for not P or Q has the same truth values as the column for not P or not Q. And the column for not P or not Q has the same truth values as the column for not P and not Q. So the column, the truth values for P implies Q are the exact same as the column of truth values for not P and not Q. So these two, we see they are logically equivalent, and we can prove that with the truth table, or we can do it with a proof like we just did here, a basic proof just with a few steps. And now we're going to look at one more term. And this term is satisfiability. And this is another term about a single proposition, P. We say that P is satisfiable if it's possible to assign truth values to its propositional variables in a way that makes P true. And one thing we can note about the definition is that a proposition is going to be satisfiable if its negation is not a tautology. And that should be an N. And here's a few observations we can make about the terms that we've seen in this video. So first, a tautology is always going to be true, regardless of the truth values of the propositional variables. A contradiction is never going to be true, regardless of the truth values of the propositional variables. And then a satisfiable proposition this is going to be true in at least one scenario. In other words, true for at least one assignment of truth values to the propositional variables. So we're going to look at some examples and determine whether or not they are satisfiable. So this first one, in order to determine whether or not it's satisfiable, we can do a truth table and we can see, is there some row of the truth table that has a true in the column for this proposition? So the truth table here will not be too large because there's only a single propositional variable. We'll have a column for P, a column for not P, and then we'll have a column for P and not P. The leftmost column, P, can be true or false. Not P will then be false or true. And then this conjunction here, P and not P. The conjunction is false in the first row because the right conjunct is false. And in the second row, it's also false because the left conjunct in that case is false. So this is not satisfiable because there's no row that has a T in the column for the proposition. Okay, let's look at another one. This one has more propositional variables, so we have more rows to do here. But we have fewer, well, we don't have more columns to do. So this is true and true, true and false, false and true, and false and false. Okay. Now we only have this last column, P and Q. And we've done this one a bunch of times. So true in the top row, but false in all those other rows, because all those other rows have at least one conjunct that's false. And for the conjunction to be true, both conjuncts have to be true. And we have this row with a T. So this is satisfiable. It's only satisfied when they're both true, but that's enough for it to be satisfiable. Let's do another example. So this is another one we've seen before. And I'll do another column on this one too. So we'll do a not P column, and we'll have our not P or Q. So the thing I claimed a few slides ago that we showed in the video from last time. So we'll do that again quickly, just so you don't have to look back at that video if you're wondering about it. So here we have P is true, Q is true, P is true, Q is false, P is false, Q is true, and P is false and Q is false. Here the not P, we got false, false, true, true. And then not P or Q. We'll do that one first. So not P or Q, first row, not P is false, Q is true, so we get true for the disjunction. Second row, not P is false, Q is false, so the disjunction is going to be false. Third row, not P is true, and Q is true, so the disjunction is true. Fourth row, not P is true, Q is false, the disjunction is still true, because at least one of the disjunctions is true. And now we'll do this middle column, P implies Q. So here, first row, hypothesis is true, conclusion is true, so implication is true. Second row, hypothesis is true, conclusion is false. P true, Q false. So the implication is false. Last two rows, the hypothesis is false in both of them, regardless of the value of the conclusion. When the hypothesis is false, the implication is true. So notice that this middle column and that last column, we got the exact same truth values. And that was what I claimed a few slides ago. So if you're wondering about it, there's the justification for it right here. And what we were trying to check was whether or not this is satisfiable. And it definitely is. We can see that there's at least one row where P implies Q has true as its truth value in this truth table. In fact, there's 3 rows, but we only needed 1 for it to be satisfiable. Having 3 is more than enough, and it's fine. It is satisfiable. And that might be it for this video, but there'll be more next time. So thanks for watching.